So hi everyone, my name is Ciarán Eising, and Jimmy asked me to come along this evening to give you a quick overview of omnidirectional computer vision. Um, we'll look at what omnidirectional cameras are. We'll look at how omnidirectional imagery kind of differs from normal imagery, and how the geometry differs, and how really we should treat omnidirectional imaging a little bit differently when we talk about deep learning networks and the likes. Maybe first a little bit about myself. Excuse me, I got a bit of a cold here. I finished my PhD somewhere around 2009. It was in the general space that we're talking about today, but more around omnidirectional camera design, optics, and calibration rather than computer vision. After my PhD, I joined Valeo, who are a global automotive components supplier. But most significantly for me, they're a global supplier of automotive surround view camera networks. It's in Valeo that I really got into computer vision. In the early years, I did a lot of work in geometry and SLAM-based computer vision, and then later on, got into kind of obviously got into more machine learning as that revolution was happening in the 2010s. So while I was successful in my industry career, I did achieve kind of director level engineering positions. In 2020, I decided to make the move back to academia and became an associate professor of AI and computer vision at the University of Limerick. Made that decision literally. I joined the University of Limerick like literally a week after our first COVID lockdown in 2020. So it was another maybe 2 years before I actually got an office here on campus. But I've continued to work since joining academia in the space of omnidirectional computer vision and for particularly for the automotive applications. Currently, I supervise about 16 or 17 researchers that are investigating automotive perception with a very strong focus on omnidirectional perception. So let's talk about what omnidirectional cameras are. Maybe people aren't aware. So maybe even before we discuss what omnidirectional cameras are, let's discuss what a normal camera is. Or more correctly, what does a normal image look like? So this is kind of the standard image from a standard camera. We all carry these around with us in our pockets. Many of us will have these fixed to our cars behind the windshield and that type of thing. You point a camera at what you want to take a picture of, and an image is captured of a small portion of the entire scene. Such cameras are mostly unidirectional, though you can have a bit of a wider field of views. But you know, it's in the direction that you point the camera that the image is captured. Most of the famous data sets we use in computer vision are captured using such cameras. So like the COCO data set is famous. ImageNet, of course, is extremely famous. And in automotive, we've the Kitty data set. And they're all kind of, let's say, nice linear images. None of them demonstrate omnidirectional imagery, though. Okay, so what are omnidirectional cameras then? So let's look at a few omnidirectional camera types, maybe. The fisheye camera is probably the most common omnidirectional camera type. It's relative low cost compared to other omnidirectional modalities, which is in turn due to the fact that it's made up entirely of lens elements. You can pick up a fisheye lens for your mobile phone for a few euro. Quality is not going to be great, but for 50 quid, you'll get a decent kind of fisheye lens for your mobile phone. They're quite common in the art scene in the 60s and 70s due to the kind of hippie-ish, kind of trippy look. But particularly in the last 15 years or so, they've made kind of inroads into the automotive space due to the extremely wide field of view and the relatively low cost, as it provides a very kind of wide. You can provide almost a full surround view of the vehicle using just a few of these cameras. Also in the robotic space, it's become very popular. So some applications, I mentioned automotive. They're commonly found in the automotive case where just four cameras can offer a full surround view of the vehicle, which is very useful for things like, standard rear view, surround view applications. So for human viewing consumption, but also in the AI space where they have made kind of inroads in low speed, particularly low speed applications such as parking, traffic jam assist, backover assistance, and so on. And in mobile robotics, they've made a good bit of inroad. For example, Dyson use a fisheye camera for the mapping and localization of their robot vacuums. We have we've mirror-based omnidirectional cameras as well. So basically, you can create an omnidirectional image by pointing a normal camera at a mirror or at a set of mirrors. The mirror can be curved, like in this case, which gives the wide field of view. Of course, a major limitation is that there is a blind spot in the middle of the image. It's basically reflecting the image of the camera itself. And typically parts of the construction of the camera, such as this kind of boom of the thing, that's also visible. They're less commonly used in commercial applications, in my experience, as they are more expensive and more bulky than fisheye cameras, and the bulk makes them hard to integrate from a design perspective. They usually use, perhaps more bespoke mobile robotics research. Camera clusters is where we get, I would say, real omnidirectional imagery, in that you can see you have one camera that sees the entire 360 in 2 dimensions field of view of the scene. However, typically how that works is by actually having a cluster of cameras, and then you stitch the images from multiple cameras together. So, for example, this Ricoh 360 camera uses 2 fisheye cameras, basically based back to back, produces 2 fisheye images, which you then stitch together into one 360-degree view. You'll often see these, if you go on YouTube, you find these for extreme sport videos. Commercially, you'll find the companies for creating 3D virtual tours use this type of camera. So real estate companies use them for mapping house indoors as well. It's kind of a couple of examples of their application space. We can get kind of more extreme than that. This camera from Panono has 36 fixed focus cameras for a total of 108 megapixel image output. So full spherical 108 megapixel spherical image output. Camera clusters work because the cameras are almost co-located on top of each other. At least the distance between the cameras is so small compared to the distance from the camera to the scene, that it allows the individual cameras to be processed into spherical image without any artifacts, such as parallax artifacts. If the cameras kind of further apart, you'd have issues with parallax. Maybe to summarize then the main types of omnidirectional camera before we move on to some of the computer vision and the geometry. So we have dioptric omnidirectional cameras based on lens only, such as the fisheye camera. Catadioptric cameras use a mirror to get a very wide field of view. Then typically panoptic cameras give a complete field of view and come from a camera cluster, 2 or more cameras. There are other omnidirectional camera modalities, perhaps a little less common, but I'll just kind of mention them briefly. You've got the single camera rotation scan, literally a rotating camera. A panamorphic imaging system. It's like a fisheye camera, but the added lens elements increase the optical resolution in one axis, so you're kind of maybe elongated in the Y dimension of the image. Monocentric panoramic systems. I don't really even know what they are, to be honest. They're kind of like these fiber bundles you use to create so instead of a kind of a lens element, you use fiber bundles to create a complete panoramic image. The advantages of omnidirectional imagery are pretty obvious. A single image captures a huge proportion of the available scene, potentially up to the entire scene in the panoptic case. The disadvantages, well, there's complexity of design and cost, obviously. Even though fisheye lenses are not particularly expensive, they're not as cheap as non-fisheye. So omnidirectional cameras are like a class of camera that can view in all directions. Not really true, as I mentioned, it's not full 360 in 2 dimensions for every camera type, but we can say that they can see a huge proportion of the scene compared to kind of, like I said, the normal camera modalities. So at the end of the presentation, I'll give a list of kind of papers that I suggest, if you're interested in it, you can kind of follow up with those papers. Maybe another type of omnidirectional camera is a camera network where multiple cameras are located at distinct but connected locations. And you commonly see this in automotive, where co-locating the cameras is not feasible because you've the body of the vehicle itself getting in the way of the co-location of the cameras. So I have 2 examples of camera networks. First is the famous New Scenes dataset, which is a network of 6 cameras located around the vehicle, 6 kind of, like I say, ordinary narrow field of view cameras. And this type of configuration is very common for automated driving. The equally, or maybe a little less famous, but quite famous Woodscape dataset from my old company Valeo is also interesting, as it's like a network of omnidirectional cameras. So it's 4 fisheye cameras located around the vehicle. So I'm going to get into kind of the computer vision, but I want to kind of highlight an optical cost as well to omnidirectional cameras. And when I say optical cost, I mean there is also a kind of a price aspect to it, but here I mean really the functional cost to it. So the optics for fisheye and for other omnidirectional cameras is a good bit more complicated than normal cameras. Here I'm going to focus a little bit maybe on fisheye, as it's probably the most commonly deployed omnidirectional camera. But you'll see similar kind of effects with other omnidirectional camera types. Geometric distortion is the most common, and I'm going to talk about that a bit more going forward in this presentation. But other problems that have largely been solved in all but the cheapest normal lenses remain as an issue for fisheye, particularly at the periphery of the image. So, for example, optical light fall off is a real problem. So, it's towards the periphery, you get basically less light hits the image sensor, and so you get a light fall off. Image sensors commonly compensate for that, but at the cost of signal to noise ratio. Chromatic aberration is particularly pronounced at the periphery. So you can see the kind of blue fringe here, and you see a red fringe here. So that's chromatic aberration. You typically won't see that in kind of standard cameras, but you will see it in fisheye, even the more expensive ones. And then there's an effect called astigmatism, which is basically where you have a different putting it crudely, a different blur in the 2 different dimensions. So there's more blur in the horizontal dimension compared to the vertical dimension here. Funnily, not funnily, these optical effects can have an impact on the performance of computer vision algorithms naturally. So in a recent work that we have just published out of my team, we surveyed a lot of these optical effects for the automotive space, and could see obviously a negative effect, sometimes a positive effect. So where we get a positive effect is where you have a depth where the network has to learn some information about depth, and where you have then things like astigmatism or chromatic aberration, which are depth dependent. It makes some sense that the network can learn stuff about those aberrations, and then that can actually give a positive effect to computer vision. But generally, when we talk about kind of the classical things of object detection, semantic segmentation, there's a negative effect from these optical artifacts. So that's just a note on the cost of omnidirectional. Okay, so omnidirectional is great. It shows us a massive field of view around of the scene, but there is a negative effect. So let's talk about geometry. I mentioned geometry earlier, and it's probably the most obvious effect of omnidirect. I mean, when you think about fisheye, it's what you think about, this weird kind of distortion of the image. Well, I mean, it's better to say that the mapping of the scene is to a nonlinear image. I said distortion there. It's not really distortion. The nonlinear mapping is a necessity for the capture of the large field of view. I like to think about the map of an Earth. We do warping from a sphere to a plane, so from the sphere of the world to a plane of our map, uh, and that messes up the geometry. Certain mappings fail to preserve certain things. Like famously, the sizes of countries can become stretched. So countries nearer the poles are increased in size on the map compared to reality on the sphere of the Earth. But we don't necessarily call that distortion in general. It's a byproduct of the necessary warping of a sphere to a plane. And the same is true of omnidirectional cameras. Uh, we shouldn't really call it distortion. Rather, it is what we need to do to map essentially a sphere of the scene to the plane of the image we're talking about. So distortion is a bit of a misnomer, but that's what we call it. So I'm going to use that term going forward as well. So the standard geometric model that we use for normal cameras is the classical pinhole model. We can imagine a plane and a projection of a point, and the where the camera captures it is on the intersection of the ray with the plane. This is standard kind of stuff. Anybody who's done any kind of classical computer vision will know this. Of course, no camera, or at least very few cameras, actually adhere to the pinhole model due to the fact that there are lens elements that introduce some deviations, and we call this deviation distortion. And typically, if you calibrate the camera, it is relatively straightforward process to remove distortion and bring the image to a place where it adheres to the pinhole projection model. For wide-angle cameras or fisheye cameras or other omnidirectional modalities, the distortion correction can be a bit weird. If you try to create the image, there could be some funny artifact in itself. First, even though we call the fisheye image distorted, as I kind of discussed earlier, the correction process can actually make things look more distorted due to the perspective. Like the people on the left of the image here, they look more natural. They look more correctly placed in the scene than they do in this undistorted version. That's because of the extreme perspective projection that we're mapping to. Here they actually look closer than the guys in the center here, even though they're actually further away, as you can see from the left-hand image. And then there's this kind of blurring that occurs, which is due to the interpolation of that remapping function. So we've to fill in. There's you don't have a one-to-one pixel mapping. So where you are missing pixels in the mapping, you have to fill it in, and you do that through interpolation, which itself causes blurring. Of course, you don't need to undistort from the center. You can undistort using different windows. Like on the left-hand side here, we can pick an off-axis window and undistort it to this view, which is kind of looking to the left of the image there, rather than straight out from the center. What people often do with omnidirectional imagery is do piecewise linear unwarping. For example, unwarping this omnidirectional image to the faces of a cube. So you can imagine multiple of these faces making a cube, and that enables us to do some linear operations such as CNNs on a fisheye image that's mapped to linear images. Sometimes you see things like mapping to cones as well, not to cones, to cylinders, which kind of linearizes the image in one dimension. For example, if you vertically align the cylinder, it linearizes the vertical component of the image. However, maybe it's a bit more interesting and a bit more fruitful to consider more native geometry for omnidirectional cameras. So what is a more native geometry for an omnidirectional camera? So I talked about the standard pinhole projection model of a camera, and real cameras have a little bit of distortion, which you calibrate to remove it to get this valid warping. We can think of this as a normalization of I don't mean to get too, and I do apologize to people if I lose you this bit, but don't worry, we'll come back to normal stuff. We can think of this as a normalization of homogeneous vectors. So if anybody knows about homogeneous vectors, what you do is you basically put it crudely, is you project your image into a three-dimensional space in which the last element is essentially one, and that defines a ray in the world. And that's one normalization process, however, and that's a kind of a planar normalization. However, we can also do a spherical normalization of the same points. And this is still a homogeneous coordinate, but spherically normalized homogeneous coordinate, where instead of normalizing, so one of the elements of the 3 vector is 1, we normalize it so it's Euclidean distance is 1. So as if the points lie on a Euclidean sphere. But in this case, we can model full omnidirectional cameras, full 360-degree cameras that we use in this model. So this is quite geometric, but we can also think about deep learning methods using this model. So let's talk about deep learning. And particularly we'll talk about convolutions, though we'll talk about transformers as well shortly. So let's talk about translation and equivariance in convolutions. This is a common property of any convolution. If we apply first a translation to the image and then a convolution, it's basically the same as applying the convolution and then a translation. The result is the same. This is known as translation equivariance of convolutions. It forms part of textbooks. It's quite powerful. It means that no matter where in the image or object appears, like this cow, we can expect our CNN, our network, to perform equally well. So it's quite powerful invariance. That's when we capture images. Often objects are in a specific orientation, for example, upright, though perhaps at different positions in the image. If we think of like a front view camera on a vehicle, the objects we observe, like other cars in the scene, or traffic signs, are typically oriented upright. So having a translation equivariance built in is powerful. There are, of course, other equivariants that will be nice. For example, there is some research in making CNNs equivariant to at least some discrete rotations, for example, a rotation through 90 degrees, which can basically be achieved by including 90-degree rotated kernels in the network. Other equivariances we expect the network to learn. Cows are deformable objects. Humans are deformable objects. They can be in different shapes and poses, and we have to expect they can be different coloring patterns and different lighting of the scene as well. And we have to expect the network learns those equivariances. So that's their examples of kind of learned equivariances. However, translation equivariance fails quite significantly for omnidirectional images. Here, for example, we have a fisheye camera in a standard surround view configuration on a vehicle. This one's mounted on a wing mirror. This is like a production vehicle. These cameras are in the wild, millions of them in the wild. The vehicle on the left over here, I've zoomed in a little bit because it's hard to see, is oriented very differently in the image compared to this vehicle here, even though in the world it's actually it's upright, it's on the ground as well, but it's completely rotated through at least 90 degrees there in the image. So the translation in the world has led to a significant rotation in our image, and so that's why you could see that kind of convolutions can fail or not be optimal in this case. Similar for security systems. Really, when you look at images like this, you realize that, as I mentioned, translation in the real world leads to rotation in the image. Because the translation equivariance in the image is essentially broken for omnidirectional cameras in many configurations, this is another equivariance that the network has to learn now for omnidirectional. So we say the network is going to have to learn translation, going to have to learn the translation equivariance now. So there's no good way to use translational convolutions to analyze spherical images, but the research community has obviously stepped up, and so let's consider the omnidirectional images as spherical images. As mentioned, the sphere is a natural model for omnidirectional cameras. In the same way that the plane of projection is a natural model for standard field of view cameras. If we have a spherical image, one option is to use a tangent plane over here. So this is proposed by the guys, Ciarán Geiger, to quote, the sphere-net kernel exploits projections of the tangent plane in in red, of the sampling patterns on the tangent plane in blue, yielding filter outputs which are invariant to rotations. Now, not full rotations, but the rotation induced by the spherical camera. So that rotation problem we saw previously is basically solved by this approach. Sue and Grauman, the guys here, I'll got the list, the full names of the papers at the end of the slides. So Grauman built on this to develop the kernel transformer network to transfer convolution kernels from perspective images to the 360-degree images, essentially meaning that you can take a pre-trained CNN on kind of originally trained on perspective images and map it to a CNN for spherical images over here. Okay. They also have the same authors also proposed two approaches to solving spherical CNNs. First one is CNN on an equirectangular projection. So this is on warping. This is like the map, the unwarping of the surface of the Earth to a map, and running a convolution on that. And then also using basically creating images of the tangent planes and running individual networks on each of those created image. The bottom one is computationally more expensive, but more accurate, and the top one is more efficient but less accurate. So summarize spherical models. I didn't talk about Taco Cohen's work as well. That's quite powerful work. Taco Cohen did work that incorporates both rotation and translation equivariance in one spherical model, and that's quite powerful. So I didn't mention that, but that's kind of a summary of different spherical convolution methods. We, of course, now transformers are all the rage. So they've become pretty popular recently. So Sungmin Cho and et al. Have looked at spherical image in transformer networks. And if you call them transformers, what you do, the original vision transformer uses image patches. So your image is patchified, and then you have a patch embedding that's passed to the transformer encoder. What spherical transformer does is map the spherical image to a icosahedral surface like this, and each surface of the icosahedral becomes one of your patches that gets passed to the patch embedding and onto your transformer. So that forms the basis, that spherical icosahedron, the surfaces of the icosahedron that fits within the sphere form the basis for the transformer's patch embedding in this case. And finally, maybe a little bit about output representations for omnidirectional cameras. Your classical kind of object detection of a bounding box doesn't really work for omnidirectional cameras because it's just not very accurate. This bounding box has a lot of error. Even though it's a good detection, it's got a lot of error in it. So there's work that we did a few years ago on this, kind of looked at different ways to represent that. So we oriented bounding box. We had a curved bounding box, and the curves followed the actual distortion of the fisheye. So that's pretty cool. We kind of played around with the idea of kind of doing elliptic representation, so learning an ellipse rather than a bounding box. Basically having a bounding box where you let the four corners of the bounding box move freely, and then basically a 24-sided polygon, which is akin to an instant segmentation. Okay, so I'm more or less at the end of the presentation. Maybe just a shout out if people are interested in omnidirectional computer vision, and if you're planning to attend CVPR this year, we have the omnidirectional computer vision workshop. It's actually the 5th time we've run this workshop. So we'll be in Seattle this year, in June this year, with this workshop. So do come along if you're interested in this type of computer vision. If anybody happens to be around Ireland as well, you're more than welcome to join us at the Irish Machine Vision and Image Processing Conference. That's another conference that I'm organising this year. For anybody that happens to be here, it's small, but it tends to be kind of a lot of fun. So with that, that's the references I talked about. So if people are interested in reading more about this stuff, I do suggest following these references. It's not a hectic space. It's not there is definitely work kind of going on in it, but maybe compared to other areas of computer vision, it's not the most hectic space. So hence some of the citations are kind of a few years old. Awesome. I'll kind of take a look at. Jimmy, sorry, go on.
Yeah, no, I was going to say that there's a lot of great resources here, and we'll make sure to scrape them all out and put them in the follow-up email, as well as links to the workshops, not just the one happening at CVPR, but also the one in Ireland for our folks that may be in that neck of the woods. So with that said, it does look like you have a few questions in the Q&A if you want to poke over there and see what's happening. I will tell you that I
Yep.
think first two questions from anonymous attendee, those came at about the time that you were showing the slide where you were talking about spherical planes, the difference between the blue and the red, omnidirectional cameras. I think that's around the point when those questions came in.
Okay, and I see they're kind of asking about the input image for the model and the architecture. I don't have all those details at the moment there because I didn't present my models. But I would point you basically at the papers here that I would have referenced in the slides as well above to get that information. Yeah, so then Bill kind of asked, you need to differentiate between 360-degree in one plane and 360-degree in 3D dimensions. Yes, of course. So that's what I was saying above, maybe when I compared, if I have the slide here, it's way back at the beginning. Here, yeah. So you have 180-degree opening angles, or a little bit greater for fisheye. You can have much greater than 180-degree opening for cathode optic, but you can have full 360 when you have panoptic. You have your camera cluster. So you're absolutely right. Different modalities give you different kind of levels of omnidirectionality. So Francis saying an application I remember in poverty reduction and international development was when Bill Clinton launches Inside Impact East Africa initiative employing omnidirectional cameras and virtual reality technologies to showcase or examine the impacts of initiatives in East Africa, raising awareness and galvanizing local sport. Cool. That's a nice story. Thank you. I must look it up. Can you explain a bit more detail about the use of transformers? I didn't quite understand what's the advantage. I don't want to go into detail, in particular as where I think I'm at the limit of my slot here. But I don't want to go into the detail of transformers. I will point you at kind of multitude of resources out there to explain transformers and how to use them. What I just wanted to hear, if you understand how transformers work, what I presented here was how you can use transformers with omnidirectional imagery. Okay.